Hi everyone, and welcome to the last part of the second day of this symposium. Remember that we have a chat to ask the speakers questions. And now we have the presence of Ángel García Chung of the Chemistry Department of the Universidad Autónoma Metropolitana, Unidad Iztapalapa, and his talk about towards entropic uncertainty relations in non-regular Hilbert spaces. So please go ahead.
Thank you, Saul, for the introduction. First of all, I would like to thank the organizers for this kind invitation to give a talk here at this symposium. The opportunity to talk a little bit about the current project I'm working on, entitled Towards Entropic Uncertainty Relations in Non-Regular Hilbert Spaces. Of course, this is a work in progress. I'm not gonna, fortunately, present definite results, but basically I'm gonna address the main ideas of this project. This project is in collaboration with Dr. Federico Sadra at University of Antwerp, Belgium, and Dr. Alejandro Corici at UAM here in Mexico. And okay, so the outline for this talk that I prepared is basically I'm going to discuss a little bit the Bialynicki-Mielczynski entropic inequality. I'm going to go over the details of the construction. Then I'm going to use this construction to motivate the goals of the current project. We will see that this is going to lead us to the geometric quantization, and then I'm going to provide a brief idea of what geometric quantization is and how is that connected with non-regular Hilbert spaces, in particular to polymer quantum mechanics. And at the end, I'm going to close the presentation by addressing the conclusions of the talk. Okay, so the uncertainty relations for information entropy in wave mechanics is a paper published by Bialynicki, Virula, and Jerzy Mielczynski in Communications in Mathematical Physics back in '75. And they obtain an inequality which is mostly related with the Hilbert spaces rather than the standard canonical commutation relations. And these entropic uncertainty relations are, in principle, stronger than the Heisenberg uncertainty relations, and that's part of the statement of the authors of this paper. And this first part of the talk, I'm going to try to summarize the main ideas behind these uncertainty relations. So the first step is to consider a state in an LP space. Here, an LP space in mathematical terms is a set of all the functions from the real numbers to the complex numbers, such that the norm, the P norm, or in this case, the A norm, is defined in this way. And this norm has to be finite for every number A. Okay, so the LA space is no longer a Hilbert space. We are not actually working with a Hilbert space, but with an LA space in this case. So the set of functions from the real to the complex number satisfying these conditions, okay, is what we call the LA space. Okay? Of course, if you have a function that is an LA function, due to A goes from 1 to infinity, okay, then any LA function is also an L2 function, okay? Because this norm, when you take A equal 2, you're gonna recover the Hilbert space norm. So every LA function is also an L2 function, okay? So the next step is to consider the dual state. So to every element on this LA space, you can associate another state in a different L space, in this case an LB space, which is the dual under this Fourier transformation. Okay, so in this case, I'm taking just H bar equal to unity. Okay, and so the idea now is that we have two spaces, the LA space and the LB space. One is defined using the, let's say, the coordinate representation. The Lebesgue measure has units of length. And the other L space, it's the LB space using the P, the Lebesgue measure with P units in this case. Okay? And then the question is, you might ask, what's the relation between the norms of these two functions? Between the function psi defined in the LA space and the norm of the function psi tilde defined in the LB space, but with different norms in this case, with different values for the A and B parameters here. And what they show is that as long as you consider this coefficient KAB to be given by this expression, and A and B satisfying these conditions such that B is greater or equal than 2, then you have that the relation between the norm is given by this inequality here. Okay? Then the next step, of course, this result is not introduced by Bialynicki, Birula, and Mielczynski. They just obtained this relation out of one of the first two references on their paper. Okay, but they just used this inequality here, which was proved by the mathematicians in prior publications, in this case, the first and the second reference on this paper. The next step is to construct this quantity here, WB, as a function of the parameter B. And this function here of the parameter B, as you can see, result from considering the right-hand side of this inequality here. What they did was basically to move the B norm of the tilde psi function on this inequality here they move it to the right-hand side, and they construct this quantity here. As a result of the inequality, this quantity is forced to be non-negative, okay? So if you move this to the other hand, you are forced to have a negative quantity here. Good, so far so good. We're using some mathematical theorems to obtain this inequality, and the conditions for these theorems to hold are basically giving us the parameter b as a free parameter in this case. The next step is to use Parseval-Plancherel theorem, which states that at 2, when b equals 2, then the norms, when b equals 2, we will have a Hilbert space properly, and then the norm of the Fourier of the function, the 2 norm of the Fourier of the function, and the 2 norm of its Fourier transform are equal, right? So if they are equal and the k parameter is 1, you can see that if a is 1 and a is 2 and b is 2, then this is equal to 1, right? So you can also check that here k is going to be also equal to 1. So the inequality becomes an equal sign condition here for the norms, in this case when b equals 2, okay? So then according to this function, w at 2, okay, is going to be 0. But if the function is going to be 0, then we can go back to the inequality and we can ask what will be the value of the first derivative of this function. Okay, and what they did is that according to this inequality, then the first derivative from the right is going to be also non-negative when evaluated at 2. Okay, so this condition is really crucial here for the outcome of the inequality, because now you just have to calculate the first derivative of this quantity bw here. If you go back to the expression of bw and you do the derivative of this with respect to b, what you will get is something like this. Is this expression here, where hx and hp equals to a relation given by this when n equals 1. Here n is the 2 norm of the system, okay? And you can see that this inequality becomes this when we take n equal to 1. So the inequality here is what is called the uncertainty relation, the entropic uncertainty relation. And what we can see here is that it was derived using just the Hilbert spaces and non-information about the canonical commutation relations is used, and any relation regarding whether you have Hermitian or self-adjoint operators, it was considered. The main construction is that these functions that we use here are functions that live in an LA and an LB space, okay? So, but this is spectacular in the sense that we are not really considering, again, the canonical commutations relation. This is rather a property of the Hilbert spaces and its dual, right? We haven't considered whether we have the X represent the X operator, the P operator, whether they are really self-adjoint or not, and so on and so forth, okay? And that's the key point of this project, because now we can think about possible applications here. For example, we were considering LP spaces in which the measure was the Lebesgue-like measure. But what about different kind of measures? For example, a d-mu measure, and a d-mu measure inspiring a Gaussian-like measure instead of the Lebesgue measure in this case. Okay, why? Why do we ask about a different LP space and change the measure in this case? Well, the motivation for this is because we know that there is not a unique representation of the canonical commutation relation. There is not a unique quantum mechanics, but in an infinity number of quantum mechanic representations, okay? The very simple example of this is that we have the Schrödinger representation in which we use wave mechanics, but also we have the Fock representation in which we use matrix mechanics, okay? So there is no a unique quantum mechanics formalism in this case, but an infinity number of them, right? And you can prove, that's what I'm gonna do later on, that if you want to relate them unitarily, okay, then you have to consider at some point a Hilbert space with a Gaussian measure. So that's the motivation. If we want to have an entropic uncertainty relation deriving the inequality following the steps in the paper I showed you before, then we can have an inequality like that, but built for all the quantum representations rather than the unique Schrodinger like with the Lebesgue measure. Okay, I'm gonna go over this part later on. How can we do that? How can we relate? How can we obtain an entropic uncertainty relation for all the possible quantum representations? Well, the idea is to use geometric quantization. I'm gonna describe a little bit later what geometric quantization main idea is, okay? And we can see that that can be cover the question we are addressing here. Of course, I'm talking about the Stone-Neumann theorems, which they state that there is a unique quantum representation which is the Schrodinger representation, and all the other representations are unitarily related with the Schrodinger representation if certain conditions hold, okay? And so what we want to do, again, is to explore the form of the entropic uncertainty relations, but not for the Schrodinger representation, but for all the possible representations in quantum mechanics, exploring this construction for Gaussian-like measures on the Hilbert space. The next step will be like, okay, if we change the measure, okay, why can we not change also the configuration space? So instead of working with the real line, functions defined on the real line to the complex number, instead of using the real line, we can use a different configuration space, like, for instance, the Schwarz space. The Schwarz space is like the Schrodinger Hilbert space for field theories, for instance, for the scalar field using particle physics, for example. And then we can ask ourselves, will it be the analog of entropic uncertainty relations for field theories, right? So that's like the next step. Not only field theories in flat spacetime, but also in curved spacetimes, because the Hilbert space used in field theory, whether flat or curved, is actually Hilbert space with this form. In the case of curved spacetimes, it's no longer the Schwarz space, but a different space. And of course, the next step will be, what about if we, instead of working with the Schwarz space and the Gaussian measure, we go to an irregular Hilbert space? An example of an irregular Hilbert space is the one used in loop quantum gravity, loop quantum cosmology, and polymer quantum mechanics, in which instead of working with the real line, we work with what is called the Born compactification of the real line, and the measure within this Born quantification is the hard measure of the circle. Okay, and of course we can also explore whether we can have entropic uncertainty relations for this Hilbert space. That's like the motivation in our case. Why? Because we are not working with the canonical commutation relations at all. We are just working with Hilbert spaces and their dual. Okay, so let us go briefly with the geometric quantization idea. The main goal in the geometric quantization is to have a closer relation between the classical description of our system and the quantum realm. Basically, a clear connection between the phase space and the Hilbert space. Usually when we talk quantum mechanics to our students, we just go from classical to quantum as a jump, and then we just introduce a phase space, and once the student is familiarized with the phase space, then we jump to the Hilbert space and everything goes really like crazy, right? Because we don't really know where does this Hilbert space is coming from, right? So the idea of geometric quantization is to smoothly connect things in order to arrive at the Hilbert space. So the idea is we have basically the phase space, which is in this case a simple example. We have the plane and we have the symplectic structure over there, which is basically the symplectic structure, which is the one deriving the Poisson bracket, for instance. Okay, we take it as a real linear space. We can add vectors in this space. We have vectors. And then we introduce what is called a linear complex structure, which is an operator such that the square of this operator is proportional to minus the identity in this case. You can see that for this vector space, the general form of this complex structure is given by this. So it's parameterized by two parameters, A and B. These A and B are rather different to the A and B I introduced before, okay? And then we can talk about the eigenvalues of this complex structure. You can see that due to the square of this complex structure is minus identity, it will have two eigenvalues, plus I and minus I, okay? But the eigenvectors are not elements of the phase space because we have complex vectors in this case and we are having real vectors here, okay? So, but we need complex vectors because the Hilbert space is formed with complex functions rather with real functions, right? So we complexify this space, and once we complexify, we are adding extra information. So we are doubling the information we have at the beginning. So we need to, again, restrict our information. But now that we allow for complex conjugation, we have to restrict, again, our information. The way we do that is by noticing that each element in the complexified version of our space can be split into the positive and the negative part. Positive being proportional to the positive eigenvalue, and negative mean proportional to the negative eigenvalue. Actually, the positive and negative part can be written in this way for every element of the complexification. And once we do that, then we just work with the positive part. In particle physics, this is called the positive frequency description of the system, okay? So we double the space, but then we restrict to the positive frequency part, and once we have the positive frequency part, okay, the space constructed with this is the one we are gonna, it has all the seeds we need for the Hilbert space construction, because now we have a complex space using the information we have at classical level. The next step is to construct an inner product in this case. We construct an inner product in this way, where the x minus here is introduced in order to reflect that we are using the complex conjugation in this case. Okay, and you can see now that I'm just using the elements of the phase space, the symplectic structure, and all the arbitrariness is introduced in the complex structure. Okay, so we have the symplectic structure, the vectors, and the arbitrariness is just given by the complex structure J. So this inner product is J dependent. And remember that J was labeled by two parameters, A and B. And then we complete the space S plus with the norm induced by this Hilbert product, with this inner product. As a result, we will have what is called the one-particle Hilbert space. So the one-particle Hilbert space that is used in standard quantum mechanics or even in quantum field theory can be constructed out of the elements of the classical phase space. And all the arbitrariness is introduced within the complex structure. So we don't have any way to fix the values of A and B. A and B are rather arbitrary here. But then we can construct what is called the Fock Hilbert spaces. Everybody's familiar with the Fock representation, right? In particle physics, in quantum mechanics, the way we construct the Fock space is using this Hilbert space, which is J dependent, and we can do this kind of constructions, the direct sum of these tensor products. We're working with fermions, we use the anti-symmetration, and if we're working with bosons, we use the symmetrized tensor product. And this is the Fock-Hilbert space used in quantum mechanics and also in quantum field theory. But then we can relate these Fock representations, for instance, in quantum mechanics, with the Schrödinger representation. You can prove that the measure in the Schrödinger representation is actually related with the J parameters. You can see that the measure we have in order for the two representations to be unitarily equivalent has to be a function of the B parameter. A is not really important at this level, does not appear on the measure in this case. So that's how you connect all the Fock representations with the Schrödinger representations. And we can map all the states in this Schrödinger representation. Here, S is basically R. And you can map all the elements in this Schrödinger representation to the standard Schrödinger representation known in quantum mechanics. Okay? And of course, so now the question is, can we obtain an uncertainty entropic relation for this Hilbert space? For example, can we go to LP spaces such that the L2 space has a measure given by this, for example? Can we do that? The goal of the project is to explore whether that's possible and whether that's gonna lead us to an uncertainty entropic relation for this representation and whether it's gonna be dependent, okay? And of course, you can repeat this process for field theory, and you will get that the measure is also a Gaussian measure in this case. And B here is now an operator, okay? That's why it is inside an integral here. And you can also go to the non-regular representations called polymer quantum mechanics by exploring the limit when B goes to infinity or when B goes to 0, for example, okay? So we can go to non-regular representations departing from the standard representation of quantum mechanics using a Gaussian measure like this. And that's the goal, right? So we want to consider whether a general uncertainty relation can be derived, okay, for this kind of spaces, okay? So let me go quickly with the general idea of what is an unregular representation of quantum mechanics. This is not really common topic. And well, the idea is that how can we define a quantum theory of gravity? Okay, gravity is a classical description of reality where we have the quantum theory, and what we want to do is to have them in common, right? There are many approaches to this problem. One of them is loop quantum gravity. The other one is loop quantum cosmology. And let's say the toy model is what is called polymer quantum mechanics. Polymer quantum mechanics uses the main tools developed in loop quantum gravity and loop quantum cosmology, but adapted to the standard lab problems we have in quantum mechanics, in quantum physics, right? And the basic idea is that the Hilbert space, instead of, in the standard quantum mechanics, the Hilbert space is a separable Hilbert space in the sense that we can count the number of basis elements we have in our description. In Fock representation, for example, we have a definite number of occupation bases, right? But in polymer quantum mechanics, we don't have something like that. The bases are no longer countable, but uncountable. So we have a map between every element of the base with the real number rather with the natural number. So we have an uncountable basis here. And the functions are defined using Kronecker deltas instead of Dirac or the standard Fock basis, which is 0, 1, 2, 3, so on and so forth. Right? We have now real numbers labeling the bases instead of natural numbers. That's why we have an irregular Hilbert space. Okay? And then the idea is we have the real numbers. We select a set of points on the real on the real numbers, and on each of these numbers, okay, we write down a complex number, which is going to be like the wave function. So the wave function is actually a collection of complex numbers, okay, and these complex numbers are attached to this, the real numbers that we selected for the lattice, okay. Of course, we want this to be a Hilbert space, so the sum of this, the square of these coefficients have to be finite, okay? And in order to be finite, we have to have coefficients that are not null, but in a countable set, or otherwise we might have problems. We cannot really express convergence of uncountable series here, okay? So that's the general idea of polymer quantum mechanics. Main problems: we don't have a momentum operator. Okay, we have a discrete space. We no longer have a continuum, and if we don't have a continuum, we don't have infinitesimal translations. And if we don't have infinitesimal translations, we don't have p operators. We don't have properly a kinetic term in this case. So what can we do? We have to work with the exponential version of the p operator. So p does not exist, but the exponential version of it does, right? So we have to work with the exponential version of the operators. And what we do is we construct a combination of these operators with these U operators in order to represent the kinetic terms in our Hamiltonians, for example. And what else? Well, the representation is no longer x and p, but x and u. And the standard representation in polymer quantum mechanics is the Schrödinger one, in which we have that the x acts multiplicatively, as is the standard in quantum mechanics, but the U operator acts as a translation operator, okay, which is also a standard in quantum mechanics. But due to we don't have p operator, we have to work with this form of the canonical commutation relations. So we have a different form of the canonical commutation relations. Now we have to work with u instead of p. And this is very interesting because this is also explored in many scenarios, not just in polymer quantum mechanics. And this is called generalized uncertainty principle, okay? Because the idea is we can now deform a little bit the canonical commutation relations, and then we will have a different algebra. And the idea is, can we detect these effects in a lab? Can we have uncertainty relations for these modifying canonical commutation relations? Okay, so this is a mark in a problem which is no longer attached with polymer quantum mechanics, but with a family of different theories called generalized uncertainty principles. So if we have something like this, then, and we can have an entropic uncertainty relation for polymer or non-regular Hilbert spaces, we are going to be able to address this problem, but for a different path, okay? And of course, now the conclusions of this presentation is that, of course, exploring the procedures described in Bialynicki, Mielczynski entropic inequality, but adapted to more general Schrödinger representations, it opens the door to many interesting questions, not only in quantum mechanics, but also in quantum field theory, for instance. From the mathematical level, it paves the way to explore this inequality, but working with LP spaces with Gaussian measure, for instance. And it will also allow us to address an entropic uncertainty, an entropic generalized uncertainty principle, for example. It will say something about causality in field theories. It might have an impact in field theory. What is the role of the vacuum symmetries? Because you can prove that the B term we have in the complex structure is actually related with the Poincaré group in field theory, for instance. And that's like the general idea of this project. Thank you.
Thank you so much, Alejandro, for your presentation. I think that is very interesting. I don't know if you have any questions in the audience. can be done in the chat in WhatsApp. Okay, thank you. And now we can pass to Rodolfo Esquivel. Are you ready, Rodolfo? Can you hear me? Okay. Can you share your screen, please?
Yep. Okay.
Okay.
Good.
We can see your
Good
screen.
evening to everyone. It is my
Okay.
pleasure to be here today to share with you some insights into how information theory has helped us to describe local and non-local phenomena in chemistry. Before going ahead, I would like to clarify the tone for this talk, rather than discussing the technical intricacies and mathematical formalism. I really prefer to present these ideas in a way that is accessible, thought-provoking, to the end of emphasizing the utility of information theory in chemistry, and showcase some applications, particularly for students who might be curious about this area, and for young researchers perhaps looking for a new direction to explore. To guide us through this discussion, I will focus on three key aspects. The utility of information-theoretic concepts in chemistry, which has been widely discussed in this meeting, how these concepts provide a phenomenological description of chemical processes, and also in the axiomatic interplay between our chemical intuition and theoretical information measures. Why use information theory in chemistry? At first glance, chemistry might seem far from information theory. After all, chemistry deals with atoms, molecules, and reactions, while information theory is traditionally associated with communication, entropy, and communication, as we know. However, chemistry is fundamentally about predicting and understanding change, and information theory provides a powerful framework for doing just that. It allows us to quantify uncertainty, measure disorder, and detect patterns in electronic structure, reaction mechanisms, and molecular interactions. One of the most exciting aspects of applying information theory to chemistry is perhaps the ability to describe both local and non-local phenomena in a unified way, as I'm going to describe here. One of the most fascinating aspects of this topic is how information theoretic principles align with our traditional chemical intuition. From intuition, we think of a chemical bond as a region where electrons are shared between atoms. Information theory formalizes this idea by showing that bonded atoms minimize uncertainty and maximize information exchange. When we describe a reaction selectivity, we often talk about stability and energy barriers. However, IT provides an alternative view. Selectivity emerges uncontrollable outcomes. Even the concept of molecular complexity, which we often associate with structure and symmetry, can be rigorously quantified using entropy and information measures, as we will see later on. This means that rather than replacing our chemical intuition, information theory reinforces and refines, allowing us to approach complex problems with a new set of conceptual tools. In this slide that you are looking at, I intend to present the fundamental quantum mechanical principles that govern electron behavior, which are represented in a hierarchical manner, but also to represent an evolutionary perspective on how chemistry has integrated concepts from quantum mechanics, particularly electron correlation and entanglement, into its theoretical framework. As you can see here, well, this is what we are used to teach in a quantum chemistry course. We begin with the principles, uncertainty, indistinguishability, antisymmetry. We talk about Pauli exclusion principle, and then we have to stop in pure states chemistry, as we know, with orbital double occupancy, of course, methods like the Hartree-Fock, for example. I'm avoiding here to talk about DFT because that's a different way to include higher correlations, as we all know. But what is really interesting here is that this allows us to describe periodic table and bonding theories, for example. But do we know that the accuracy of the calculations are not really good? So in those old days, before entanglement and non-locality, we were used to talk about better wave functions, like the ones of CI, configuration interaction, coupled cluster, in order to achieve experimental accuracy. But something was missing. We didn't know anything about entanglement. It wasn't established itself as a robust phenomenon. And well, we always talk about electron correlation. But the physical phenomenon was not yet experimentally demonstrated until 1981. That was the picture, I will say, 20 years ago. We all know that Albert Einstein's contributions to quantum mechanics were decisive, and not only the corpuscular nature of light was incorporated, but also entanglement through the EPR paradox. The Nobel Prize was, as you know, was awarded to Aspect Salinger and Closer in 2022. And well, there is no doubt about quantum entanglement anymore. So that the diagram that I presented before can be complemented. And now we can say that aside of locality, we have to teach non-locality through quantum entanglement. For that, it's necessary to have a coherence. And in chemistry, we incorporated all of that into mixed states. For that, we in chemistry, theoretical chemistry, have a vast experience, I would say, from since 1950s. We all know these methods that incorporate correlation. And now we can say we were incorporating not only correlation, we were incorporating entanglement. So I would say that the diagram is now complete, and I would like to represent that through this ancient serpent. And the circle is closed now, right? And as Blatko was sharing to us yesterday, we can say perhaps that entanglement is the source of everything. Classicality, for instance. Well, but that's a philosophical kind of question, and I'm not going to go into that. Well, as we all know, technological advances are now forwarded through the quantum 2.0, let's say that, technologies, which incorporate quantum entanglement. Quantum 1.0, well, that's the technology we are enjoying nowadays. And chemistry is not out of these advancements. So in these slides, you can see here some of the technologies that we have achieved and the ones that are in developing nowadays. And in chemistry, well, all of that is under development. Hopefully, in some years, we will be able to enjoy all these technologies, like the ones I'm representing here. Okay. But quantum information sciences, of course, are the base of all that technology. And all these sciences can be called now quantum sciences, like quantum chemistry, quantum information chemistry, quantum information biology, and undoubtedly, well, physics has developed all of that since, I would say, some decades ago. So in chemistry, well, we can now talk about electron correlation reaction mechanisms, molecular interactions, molecular partitioning, and can be explained through quantum information. So this new, I would say, this emerging field of research has been developed during the last years. And for that, we require, well, information-theoretic tools from not only the classical side, but also on the quantum side, like you can see here. I'm going to present some results on both sides by using all these IT mechanical, quantum mechanical tools like Shannon entropy, Fisher information, disequilibrium, statistical complexity, and from the quantum side, well, the well-known von Neumann entropy and linear entropy, for instance. The information-theoretic concepts that have arisen since those advancements in quantum information theory, we can now incorporate entanglement, statistical relations, non-locality to the, I would say, to all the knowledge that we have in chemistry. Aside of all that we have known about the classical perspective, with concepts such as the localizability, order, uniformity, the localization through the dyads of information measures, which are called complexity measures. Okay, this is a slide where I can you can see some of the applications that we can achieve through local chemical phenomena like bond strength, local reactivity, electron density distribution, and the non-local ones that include dispersion forces, the localized electron systems, quantum coherence, of course, and there are many applications in quantum, in chemistry and biology, like we're gonna talk about a little bit more. The local measures are very well known. I don't have to go into that in too much detail. Shannon entropies are very useful in both spaces, not only to account for, let's say, the localization and uncertainty, but also measures of kinetic energy from the momentum density. In contrast, we can use, this has been discussed very deeply during these meetings in the morning. We can use Fisher information in order to account for all these phenomena that has to do with fluctuations of the distributions. And disequilibrium is also a very important property in order to grasp the properties like uniformity of distributions. In case of complexity, well, we can always measure both concepts in terms of coupled information, let's say, measures, the localization and uniformity and order uniformity in this equations. You can see how to do that. These local measures of information in the case of the classical information theory account for very interesting properties, very interesting concepts like localizability, order, probability, complexity. These quantities seem, according to the research we have performed during the years, seem to be sufficient, necessary to characterize phenomenological properties of chemical, physical systems and the processes that they undergo. Well, non-local measures of information, of course, have to do with fundamental entropy. There are many others, but the ones we have used are these ones, and linear entropy, and the corresponding type of the entropies, the measures of entanglement. The applications that we have explored have to do with entanglement, chemical reactions, molecular partitioning, IT chemical space, chirality, and many others. But I'm going to talk about only a few of them. This morning, Mojokoyani talked a lot about this kind of analysis, which has to do with what we call the transition region, which is a very important part of the chemical information in the pathway of a reaction. That is almost completely blind to the energy, as we have seen. Instead of, in contrast, the entropy is a very illustrative way to grasp all the concurrent processes that we can measure from a reaction. You can see here, like Mojokoyani did this morning, that we can describe very well the bonding regions, bond forming and bond cleavage regions, and also the reservoirs of the energy that are required to bond breaking, for instance. And not only that, we can account also for spin coupling and also charge transfer processes, and so on. This is only an example. As I said before, I'm not going to into the details, but it's important to see that this can do with these measures, in this case, are the Shannon in conjugated spaces. More important or more, I would say, complex examples are done here, why in the case of the exchange reaction for methane, or even in the case of more complex reactions like the one of xylylene, in which we can describe and characterize some complex reactants. We can also describe the mechanism of the reaction in a very precise way with the use of information theory. Well, also in local phenomena, we are only representing here local phenomena. We can use these measures in order to account for the information of systems in a 5D space. You can see here this kind of representations. In the axis, you have Shannon, disequilibrium, Fisher, but also we have represented here the complexity through different colors and different sizes, for instance. And it's very interesting that in these diagrams, I'm representing all the elements up to 103. And you can see here that all these elements follow a shape of a spiral, which are theories that have been proposed before for the periodic table. So it's interesting that information theory can achieve this kind of descriptions in a very natural way. For molecules, the description is more or less the same. We can assign a specific space in information theoretical space for any kind of molecules, which means that information theory chemical space can characterize molecules in a very accurate way. Well, one of the achievements that we have recently published has to do with separability, and we have incorporated, we have justified these atoms in molecules approaches. One of these is very common, the one of Hirschfeld, also Bader, and we have been able to describe in a very rigorous way which principles are needed in order to justify these kind of schemes. We have to do with minimum relative entropy principles and extreme physical information principle in the case of Fisher. With that, the result that we have obtained for Hirschfeld and that we have justified the iterative stakeholder partitioning scheme by using Sherman-Mittal entropy in the case of Bader atoms chat is joined. We have used extreme physical information in order to justify that also the atoms obey the same conditions in the zero flux scheme, with the advantage that we don't have to use the shrinkage variational constraint. It arises in a very natural way. This was recently published. And one of the atoms and molecules schemes that are very useful too is a quantum one that was published many years ago by Dean, but wasn't associated with atoms and molecules in terms of quantum information. And that was also one of the achievements that we made. Well, one of our nice studies that we have published recently has to do with the homochirality of biological molecules. As you know, this homochirality is very important for pharmacological molecules. And sugars, for example, are of the R form. I mean, they have activity in the right form, and also in the left one, we have the amino acids. And we have seen that if we represent the normal derivation modes of a chiral molecule, of course, by doing some perturbations in every of the normal modes of this model chiral molecule, which is not an amino acid, I should say that it's just a model molecule, we can measure the entanglement of these normal modes of this. I guess it's something like 300 molecules, and by decoherence, which means that the molecules are interacting with the environment through radiation. These molecules decohere in a way that we produce all these molecules, RNAs, and also some other ones that have different geometries, and most of them have been dissociated. But the ones that are important are the RNAs, and if we account for all the contributions from these molecules, we can see that there is an excess of one of them, which shows the symmetry breaking. Well, I don't know if I have some time. I don't think I have time, but I will conclude saying that local and non-local aspects of chemical phenomena have shown that information science is shaping a new scientific language. Several of the insights presented here have not been accessed through standard methodologies, and this emerging language is founded on the axiomatic interplay between chemical intuition and theoretical information, which is shaping what we call quantum information chemistry. Thank you very much for your attention.
Thank you, Rodolfo, for your talk.
Thank you very much.
With this presentation, we finish the second day of this symposium. Remember that we have a chat in WhatsApp to ask speakers questions, and we look forward to seeing you tomorrow. Thank you.